Okay, in this video we're going to look at Gauss's law with planar symmetry. So in terms of planar symmetry, we're looking at a conductor, all right, at first, that is a thin plane of charge. So if I was able to plop some charge on here, it would spread out evenly over the entire surface, just like in any conductor. So we'd have a flat sheet, and with Gauss's law, this is an infinite flat sheet to the point where we're really just looking at points on this sheet that are or around this sheet that are very, very close to the surface. Imagine just putting your face as close to a piece of paper as you can, and you won't be able to see the edges. The sheet of paper kind of looks infinite from that perspective. All right, so if we put some charge on here, the charge will spread itself out equally all across the surface, and it will sit on the top and the bottom of that surface. Okay? Not my best, but and because it's positive, we have field that is going to radiate away. So at all points, we have an electric field that is going away from the surface due to those positive charges. All right, so I'm just going to look at one section right here. And it's also going to be going underneath the surface as well. All right, all the way back. Just like it would be if it was a wire. Okay, the wire radiates field in all directions away from it. So here, it's just going to be perpendicular to the plane. Now we can apply Gauss's law just the same. Okay, we're going to have a two-dimensional charge density placed on the sheet, and that two-dimensional charge density is the total amount of charge over the total amount of area. Now we can block off a small section of the sheet right there. All right, and that can just be labeled as A, some small portion of the area of that sheet. And if we were to draw our Gaussian surface some distance above the sheet, some distance h, all right, we're going to be able to figure out what the strength of the field will be at that height above that sheet. Now, since the field is both upwards as well as downwards, we will also have our Gaussian surface extend below that sheet as well. Now, the field is only going through those end caps right there. Okay, there is no field going through the sides of that Gaussian surface. The area at the top and the bottom is equal to the area of the section of the sheet that we're looking at. So we are enclosing an amount of charge within that area right there. And it just so happens that the flux, the area that the field is going through, is the same value as the area of our portion of our sheet. That makes this fairly easy to solve. If we then apply Gauss's law, all right, we will just have to substitute in for the charge that is enclosed. All right, so charge enclosed is equal to the charge density times the area over epsilon naught. And now we have field that is going through the area of our Gaussian surfaces, right? So field going through that part and that part. Now they're both going in the same direction as the normal to those surfaces, right? So since they are in the same direction as our normal, the dot product goes to 1. and we have flux through that area and flux through that area. So we have the same strength of electric field going through the area of the top and the area of the bottom. So we end up with 2 times that area is equal to sigma times that area over epsilon naught. The areas are the same, so they cancel out. The strength of the electric field is equal to sigma over 2 epsilon naught. Now if we look, sigma is a constant, epsilon naught's a constant, 2 is a constant. So what that's telling us is that the strength of the electric field above and below a thin plane of charge is constant as we move away. So if we were to graph the strength of the electric field as a function of the distance that we are away, it would remain the same value as long as we're considering this a relatively infinitely large sheet of charge, or staying very close to the surface of something that we can measure the dimensions of. So we have a constant strength of electric field for a thin sheet of charge. If we were to look at this sheet on edge, kind of just taking whatever the three-dimensional look is to it, and just looking at it like it looks like a wire, just like that. All right, so we take that sheet, and that would have our positive charge density on it. All right, that field would irradiate above and below, and it will be perpendicular to that surface. So we can look at our Gauss's law, our Gaussian surface, a little bit differently. If we wanted to use, the height above and the height below, our Gaussian surface can just be drawn like that. All right, and we know that this is the area that the flux is going through. We know this is a two-dimensional space. Okay, so the area there is equal to the area there is equal to the area there, and we just know that all of the field is going, outward from that surface, giving us a dot product that is equal to 1. If we had a second plate below, and maybe it was negatively charged. Now, negatively charged has fields that go towards it, right? But before that, let me do this as well. So remember, the field doesn't stop. The field extends out into space, right? Infinitely. All right, so that's just the positive field from the positive charge density. So now, if we use the darker color for the negative charge, right, so this has field that is going towards it. And this has field that is going towards it. But it does still extend beyond the other plate, right? So here we have field going towards that plate, here we have field going towards that plate, here this field is still going towards the plate, right? Another line, field going towards the plate, still going towards the plate, okay, towards that plate, towards the plate, and towards the plate. And what we're going to see here is that the field that's pointing away from the positive and the field that's pointing towards are going to cancel out. So the field from positive sigma plus the field from negative sigma is going to end up equaling 0, because vectorially they're pointing in opposite directions, and the fact that the strength of the field is constant at all distances away causes them to be equal and cancel out. Whereas in between, we end up with both fields acting in the same direction. So in between here, we have 2 times what the field would be of one plate, right? So 2 times sigma over 2 epsilon naught. That's a 2. All right, so we know that the electric field now will be twice what that is, which is just sigma over epsilon naught, since the 2's cancel. All right, and also down below here, they cancel out to be equal to 0 as well. So there is a simple planar symmetry for Gauss's law. Of course, this gets more challenging by making it have extra dimensions to it. So we can give it some thickness. We can make it an insulator with a charge distribution, and we have to make sure that we can apply all the other strategies we used for the cylinders and the spheres to the planes as well. We'll look at that in another video.